Let us start this lecture with thought process given by Elon Musk. As you heat up the planet, it is just like boiling pot that we could experience nowadays. And if you recall that in the last lecture we looked at how to take care of the effect of real gases in calculating the properties, right, and using a model known as Lennard-Jones 612 potential model. And we also looked at how we can calculate diffusivity of a IS species, particular species, in the mixture of gases. And we will also look at now how we will take care that in the thermal conductivity. In the similar manner, we can determine the thermal conductivity K by using LJ model, potential model, right. What is that? LJ means Lennard-Jones potential model, as K is 25 by 32 pi mkb T divided by pi sigma sigma AB square into 2.2 star CB by M AB. I think I need not to use because as a AV as such. So, if you look at, like, we can look at this, and what is the difference? Difference, if you look at only, this is the what you call integral constant, right, function. This difference is the collision integral correction factor, right. And for practical purposes, if I say equation 1 becomes K is 8.323 10 power to minus 4 root over T molecular weight two by 2 star, and this will be joule meter Kelvin second, right, and where T is in Kelvin, MW is in gram per mole, and sigma is in nanometer, right. So, this is of course, if you look at, it is corresponding to one species, but there might be several of them, right. So, you need to calculate the mixtures, right. So, thermal conductivity of of a mixtures gaseous mixture consists of different species, right, can be determined by using following empirical relationship. keep in mind that in the text there are several, in the literature there are several empirical relationships are there. So, I am just using one of them, right. K mixture I is equal to 1 number of species, right. Ns is the number of species, K I divided by 1 plus sigma x j 1.065 phi I j, and K I is basically K I is the thermal conductivity of ith species, and xj is the mole fraction of jth species. Right, and keep in mind that j is not equal to I. Okay. Let us say you are considering methane, you should not consider methane in these terms in the denominator, right, when you are summing it up, you should not take. And this phi Ij is again another semi empirical formula you are using, divide by 2 root over 2 1 plus mw I by mwj minus half into 1 plus mu I mu j half nwj mw I power to the 1 by 4 square. And if you look at this is a basically correction factor, which depends on the coefficient of viscosity. That means this mu is viscosity, right. Right, and also it depends on the molecular weight of the, and this mw is molecular weight. So, keep in mind that this is a formula which you can use for finding out mixture, but the error, if you it will be involved in this relationship. Let us say if I say this is 2 and this is your 3, what will be error here? Error in this will be around something 5 to 10%. Are you getting? In each step we are incurring some error, even if you are doing a very nice computation or the kind of things. So, in the similar manner we can also look at the viscosity. Mu of can be estimated as per Jones potential as mu 5 by 16 pi m kbt pi sigma square 2 by 2 star, right. And only difference is this one, that is your integral factor, right. And for practical purposes equation 1 can be rewritten as 2.6693 10 power 8 MWT. So, this is molecular weight into temperature, sigma square 2 comma 2 star, and this will be kg meter second, right, this unit. So, I mean, we can also now find out in the similar manner, like using a semi empirical relationship for finding out a viscosity of the mixture, right. Of gaseous mixture can be determined as mu of mixture 1 I is equal to 1 to ns. Ns is the number of species. This is mu I divided by 1 plus sigma xj xi y ij, and j is not equal to I. Okay. And already I have this given a relationship for the phi ij, which is same for both the thermal conductivity and viscosity. This phi ij, right, is the correction factor which is correction factor which was already mentioned earlier for conductivity, right, conductivity of mixture. That already same relationship can be used, and keep in mind that when you do this thing, this error, what you will get is something around 5%, right. That is the error you can get, less than, in the range of 5%, not exactly 5%, okay, the range of 5% you should expect. So, by this you can find out basically mixture, viscosity of the gaseous mixtures, right. Now, if you consider that one thing I want to summarize now, and look at that diffusivity what we have considered, right. So, if you look at the mass diffusivity we have considered, because there will be something concentration gradient, right, is not it? Because of that there will be diffusion process taking place, but there will be some diffusion process which is due to the temperature gradient, right, yes or no? And there will be also some kind of energy transfer due to the concentration gradient, that we have not looked at it, like consider. But in some of the combustion problem, particularly the thermal diffusion, the diffusion of mass due to temperature is being considered, right. So, let us look at that. That is basically what I had told you, that effect is known as the Soret effect, and this is due to the temperature gradient, and this Soret effect is also known as the thermal diffusion. And there will be also the what you call because of the concentration gradient, right, there will be some energy transfer will be taking place, or transport of energy, that is known as Dufour effect. And Dufour effect generally is negligibly small in combustion problem. So, DIC is approximately 0 for combustion problem. However, this DIT, that is Soret effect, has to be considered, particularly when you are using the hydrogen oxygen system, where the hydrogen, right, H and some other molecules, right, will be having some effect, like because those are lighter molecules. Lighter molecules, you know, will be travel due to the temperature gradient. So therefore, the Soret effect has to be taken care. So
natural convection type.
Which one?
Soret effect.
No, it is not natural convection as such, right? But however, because of, you know, one molecule, you keep in mind that, let us say propane. Propane is a heavier molecule, so it will be traveling at a lower velocity as compared to hydrogen or the helium or the, you know, H radical. So therefore, what will happen in combustion problem, because the temperature will be there will be temperature gradient, and that will be order of something 2200 to 300, you know, that kind of grade. So therefore, those molecule will be moving towards, you know, some place where, you know, like kind of things where the, as a result, there will be some super adiabatic temperature will be coming. That means you will get a local temperature more than the adiabatic, you know, kind of things, which we had done some computation in our as a part of our research work. We found it's quite interesting. So, but those things will be you know, will be more predominant, particularly hydrogen oxygen system or air system, you can say. So therefore, when we will consider that this effect, then we will have to consider the total mass diffusion, right, total mass diffusion kind of things, right, of, let us say, molecules A or IS species, right, due to two effects. What are those things? One is, or maybe I will write down in the next. So if you look at that total diffusion, right, total mass diffusion of IS species, right, is equal to, let us say, m dot I, right, m dot I. So what it would be then? We know that is di rho dyi by y plus, there will be also a Soret diffusion by T into dt by dy. Okay. Now I can of course write down this as di rho yi xi dyi by dy minus dit by t and dt by dy. If you look at what is this, xi is the mole fraction of IS species, yi is the mass fraction of JH species. And rho is your density, and dit is the diffusivity due to what? Due to Soret effect, right. Soret effect means it is due to temperature or thermal diffusion, whatever we call temperature gradient, and di is your mass diffusivity, whatever we call due to concentration, right. This is the mass diffusion, right. And if you look at, this is generally being considered, that is the Soret effect, and the Duffer effect, which is energy transport due to the concentration gas gradient, you know, is not being considered. And there will be also some mass diffusion due to the pressure, that also is not considered in combustion. Okay. So now you know, like the mass diffusivity and is due to the Soret effect and also the pressure effect, but we are not considering Purcell effect. Soret effect will be considered and the Differ effect is not being considered. So, with this we will now move into basically the governing equations, right, and keep in mind that I will be also revisiting this mass diffusion or the mass transfer, particularly when we will be deriving equation for species conservation, right, or species transport equations. So, now we will get back into basically fluid mechanics part and we will be looking at the mass conservation equation, right. So, with this we will stop over here and then we will continue in the next lecture. Okay, thank you.